Okay, hi everybody. My name is Sarmiento, and it's a pleasure to present this work titled Barkhausen Noise and Skyrmionium-to-Skyrmion Transition. This research is performed in collaboration with Professor Alberto Pasos Guimaraes. This is the highlight of outline of my presentation. First, I will introduce some concepts about the Barkhausen effect and skyrmions. Then, since this is a simulation-based study, I will present our system of study. Then I will present the results. And finally, I will highlight the key findings so far. Well, the Barkhausen effect was discovered by Henrik Barkhausen in 1999. Essentially, when it's applied an increasing magnetic field in a sample with aleatory ferromagnetic domains, the magnetization curve presents a steps-like behavior like this one. This behavior is due to the alignment of the ferromagnetic domains. This phenomenon is known as the Barkhausen effect. Well, now let's see at the skyrmions. Skyrmions are characterized by the rotation of the magnetic moments. Based on this, are known two types, block skyrmion and nail skyrmion. In block skyrmion, the magnetic moments rotate perpendicular to the radial directions, while in a nail skyrmion, they rotate in radial planes. These fascinating structures could be stabilized in different ways, as it is described in the literature. But here we are focused on this Zaloshinsky-Mori interaction. This interaction arises from the lack of inversion symmetry in the interface of a heavy metal and a ferromagnet. Here in this image, you can see the interaction of the large spin-orbit coupling of heavy metal with the magnetic moments of a ferromagnet. This interaction is the Zaloshinsky-Mori interaction. Well, let me introduce we are performing micromagnetic simulations in μmax3. In micromagnetic theory, the length scales are large enough to ignore the atomic structure, but are small enough to result magnetic structures like skyrmions. Here you can see our system of study that is a nanodisk with a diameter of 150 nanometers and a thickness of 1 nanometer. The material is cobalt, and the Zaloshinsky-Mori interaction could be induced by platinum substrate. In these images, you can see the skyrmion and skyrmionium where the topological charge is plus and less 1 for skyrmion and 0 for skyrmionium. These values could be determined or calculated with this definition. We are interested in disorders, so we use the Voronoi tessellation method to artificially create domains in the nanodisk. At the same time, we can modify the magnetic parameters in the between domains. And here, our goal is to study the effect of disorder in the skyrmionium to skyrmion transition. Let me present the results. Here you can see the initial parameters used in the simulation. Some of them were taken from literature. In the images, you can see the stability of skyrmionium, where for different disordered systems. Okay, we varied this Zaloshinsky-Mori interaction, the saturation magnetization, the uniaxial anisotropy, and all these parameters together. It is important to mention that all these results share the same domain pattern. So we can compare between them. As you can see, for the uniaxial anisotropy and all the parameters together, we are observing a a high modification on the shape of the skyrmionium. After that, after the stabilization of the skyrmionium, we apply a quasi-static magnetic field to induce the transition from skyrmionium to skyrmion. This could be observed in this graph of the topological charge as a function of the magnetic field. Here, different colors represent different disorder systems. These simulations were done at 0 temperature, and you can see that different system transition at different magnetic fields. In this graph on the right, you can see the magnetization in the z-axis as a function of the magnetic field. Again, different colors represent the different disorder systems. And the steps in the magnetization curves are the Barkhausen jumps. In this slide, you can see more clearly how the skyrmionium evolves when increasing the magnetic field. And the Barkhausen jumps here are due to the pinning effect of the domain walls. Well, after observing the Barkhausen effect, we repeated this experiment for different domain patterns, and also by increasing the strength of the disorder from 15 to 29%. And it is shown in this graph of the magnetization in this z-axis as a function of the magnetic field. It is important to mention that we confirm in all of the experiments the Skyrmionium-to-Skyrmion transition. Here in each graph, the black line represents the strength of the magnetic field necessary to induce the transition, and the width of the sky blue region represents the standard deviation. Based on these results, we can see that with a higher strength of disorder, for a higher strength of disorder, we need a higher magnetic field to induce the transition. Finally, by analyzing the last results, we create this graph of the frequency of the Barkhausen jumps. Here, every color represents different disorder strengths. And typically in the literature, other disorder systems show a power law distribution described by this equation. But in our case, we are observing two behaviors. Up to 28% of disorder, we observe a single peak for mid and high values of jumps. And for 29% of disorder, we observe more than one peak. Here, it is important to mention that we cannot stabilize a skyrmionium structure for a higher strength of disorder. In summary, we observe that by increasing the strength of the disorder, we can increase the stability of the skyrmionium by raising the height of the energy barrier between the skyrmionium and skyrmion. Also, we observe that the pinning effect, the Barkhausen jumps are due to the pinning effect of the domain walls of the skyrmion and skyrmionium structures. And finally, we observe two behaviors in the frequency of Barkhausen jumps. At the moment, we are trying to understand these results. This is the bibliography used in the presentation. And I want to acknowledge to the organizers of the conference, to the Brazilian Center of Physics Research, the Ministry of Science, Technology and Innovation, the PCI program, and to my collaborator, Professor Alberto Paso Guimaraes. And if you want, this is my contact email, and any comment and suggestion is welcome. Thank you.
Thank you so much for your talk. If anyone has a question, feel free to unmute or raise your hand. So I have one question, and bear with me because I'm not I don't do simulation or theory. So the disorder you're talking about, you are basically creating disorder just by having more domains present in the simulation? Okay.
Yeah, that's right.
And then do you have to, when you set up your simulation, are you worrying about the, I guess like how that changes as a function of like your material thickness or anything like that that might affect like the pinning that you were talking about from the Barkhausen jumps or
yeah, this behavior of the increasing of the thickness of the material could be understood as modifications of the magnetic parameters. That's the reason because we modify the magnetic parameters between the domains created.
okay.
I don't know if it was clear.
No, that I appreciate the clarification. Thanks. We have time for one other quick question. Okay. With that, thank you so much.